I audible now? Yeah, perfect. Okay, thanks. It's a pleasure to be here at Perth and talk about some of the architectural challenges we faced when we went through this process of the exascale procurements in the US. And so what I thought I'll do today was talk you all through the design process that we went through in that time frame, and then convince you guys that exascale is not all about exaflop, and that it's going to be about a few things that I'm going to talk today. So as I was introduced, I work in the CTO's office, and I get into trouble because I say futuristic things that may or may not be plan of record. And so this is a slide that keeps me safe, and it's from the lawyers. And so, like I said, I do want to start my talk with a slightly controversial statement that exascale is not about exaflop, but it's about different kinds of workflows that's going to happen on the exascale machine. So traditionally, when you think about computing, you're normally thinking about the scientific models, solving PDEs, solving ODEs, and so forth, right? And so what's going to happen in the exascale era is that that's going to continue a little while. You're going to think about multi-scale models. You think about multi-fidelity models. The resolution that you're going to be able to operate is still going to increase and so forth. But what's also going to happen is that you're going to start thinking about making it much more efficient using some of the machine learning techniques that Rob was talking about. You're going to start mixing and matching how data flows. If in the HPC world you were thinking about doing simulations that then write to disk, now you're starting to think about take the data that's in disk back into your machine, do some of the analytics work and so forth. So if you thought resolution fidelity was important in the scientific model space, you're starting to think about predictive accuracy and fault tolerance more important in the analytic phase and so forth. And so given that situation, so the way we started thinking about how this convergence was going to happen was along the different levels of maturity that I have listed here on the slide. So if you think about use cases in the exascale era, where you're going to have modeling and simulation consistently being run, that's what your HPC machine is for. You're going to be spitting out data. That data needs to be compared at a later point with some experiment that's going to be collecting supporting evidence for your simulation or supporting evidence for what you're trying to come up with in terms of a hypothesis. So when you think about what happens, we had to start rethinking our strategy about the life cycle of data is more key to building a system and architecting a system than thinking about just the compute requirements or the storage requirements. So we thought about it from 4 levels of architectural maturity. The first one was, can we just take a system, just build one system that'll run the HPC codes correctly, that'll also be able to run big data frameworks, and then can do AI workloads as well. That was the lowest hanging fruit. And then the second level we thought about was, can we make that productive? As in, if I'm running a big data workload on a HPC system, am I getting my value for the dollar that I'm spending there, or am I just wasting my time? And this is, am I playing games, to use Rob's sentence. The third level was, now I can run all 3 software stacks, but now if I wanted to scale any of those to the desired accuracy, the desired latency I want, can I do that on the same machine? So that was level 3. And level 4 is where we get to run the race, right? So can we beat China to become the exaflop machine, the one that has the largest one? And at least that's what was happening in the US. And so if a customer walks up to us and says, I have a workload that I need to scale up and be the Gordon Bell Prize winner, can I do that? And how do I build that top performance system? And so if in terms of mathematics and objective functions and so forth, if you were to think about, what are we architecting our system towards, we came up with a list of things that were important for the HPC folks and a list of things that were important for the big data folks. And so what you're seeing here on the slide is how do we typically do our procurements on the HPC? We start thinking about performance per dollar. Is the latest processor going to give me the maximum number of flops I can pack in a node? And can I build a big enough machine with many nodes that, given a budget, I'm able to get the maximum number of flops from it? The second one is I want the money I spend towards the insight. I want to be able to maximize both my user productivity and the computational productivity. And so what that means is that you're trying to somehow keep the weirdness of architectural diversity. So which is saying, I'm going to go move from Intel to AMD, but then the cost of me putting code from Intel to AMD is going to be X dollars. You want to make sure that the requirements from an architectural diversity perspective and the community being able to adapt to that new architecture stays within a budget. And then Tricia is going to talk about some of the benchmark performance later on. One of the requirements was to make sure that the new system runs X times faster than the previous system. So you want to prove that. And eventually, if you're setting up a facility with HPC needs, you're not just using the machine for one code or one workflow. You probably have 50 codes all the way from Monte Carlo simulation to density functional theory on the other side. You want to make sure that when those 50 apps run on a system, you're actually minimizing the variance of app-to-app performance as well. And then there's the usual stuff about, you want a reliable system, you want to conserve power, you want to be able to make sure you have people that support the resources and so forth. So if you look at the world to the commercial side that builds systems for AI, the cloud providers, the hyperscalers, and so forth, there it's about maximizing the ROI per byte. So if I have an exabyte of data, am I going to make the most money out of my exabyte being over there? And how do I build systems to make sure it delivers services on the data in a reliable way? There, your functions are slightly different. Now you're thinking about data being persistent and not just stored. It's going to be constantly used, constantly queried. And so you have to make sure when you're feeding data, you're able to satisfy cap theorem in multiple formats and multiple ways and so forth. What was also important was the community grew very fast, and most of the tools are open source. And so you have to support the ecosystem of different tools that different people would want. And then we wanted to think about, it's not codes that live for 30 years. These are codes that move really, really fast. And so you have to start thinking about, for people developing on a laptop, to quickly start running on a machine should be very, very trivial. And then this, again, goes back to some of the examples that Rob was talking about. And the key factor that we really had to take into consideration was bringing in security that's required for multi-tenancy and so forth. But then if you thought about both of these, the previous slide I talked about, the figure of merit after you build the system is, are you in the top 500? And how many people are using it? Are you using the system 90% of the time? And are scientific insights coming out of the machine? Versus over here, it's about, can I offer multi-tenancy? How easy is it to use? Can I get to the accurate model the fastest and so forth? And so if you thought about how would you construct a system today, it's a tale of two ecosystems, right? And this is a slide from Jack Dongora as well. And if you think about the differences, it's cutting across many, many dimensions. And I picked 6 ones that I've personally worked on while at Oak Ridge National Laboratory. So the bottommost level, their architecture different. So fault tolerance versus performance, you always make a trade-off over there. So you have some architecture differences that you have to take care of. The way you even launch jobs, that's the resource manager and job scheduling components. And then there is the access policy mechanism. So if you're building a HPC system, you're probably biasing your users towards using much more strong scale codes. You're encouraging them to use most of the machine in one single job and so forth. Versus in the data access mode, you want some parts of your workload to be persistent. The way you program, MapReduce versus multi-threaded ways of doing things. The choice of languages, C++, Fortran versus Python and Scala and things like that. And then the expectations of performance. In a big data world, feasibility is already great, right? In our world, when we say HPC and performance, you want to eke out the last possible thing you can from the system to make it look good, right? And so with that introduction, I wanted to talk a few more minutes about how did we approach convergence? So how are we solving some of these problems, and then walk you through what we've done. And so if I were to read one sentence about what's happening with the XXL era, I'm going to say that Shasta is our solution to it. It's a code name for a supercomputer. That is one system to run scale jobs reliably, one system that will support multiple processors and architectures from multiple vendors. It'll be one system that integrates your storage ecosystem with your compute ecosystem as well. And then it's going to be built based on an interconnect that gives you the HPC capabilities with Ethernet compatibilities. And so that's our secret sauce, and that's the Sasha system, and that's how we won 4 different the proposed procurements that they came out in the US, each one of them with a slightly different storyline. NERSC is a facility at Lawrence Berkeley National Lab, and they have about 3,000 users trying new things for the first time. They break the system all the time. They're developing new codes. They're always trying to push the boundaries a little bit further than most others. Argonne and Oak Ridge are leadership computing facilities, which means workloads that could use 20% of the machines are encouraged more than single node jobs. And so for NERSC, we had to design for throughput. For the other 2, we had to define for capability. And then towards the end, you're seeing building a system for nuclear non-proliferation activities that's one single app that you want to scale for the entire big system, right? So we were able to take one architecture that we kind of designed, and then by swapping the different components that go into it, meet different requirements. I'm going to walk you through how we accomplished it, and it's more of a story than just the components that I'm going to talk about. In 2012, Cray first came out with a product called Eureka GX. That was our first foray into trying to understand what are the requirements for data analytics. So it was taking the software stacks that were getting published out there, the Apache Sparks, the Hadoops of the world, the TensorFlows of the world, and so forth, and figuring out if we had a HPC interconnect and put it into some of these clusters that are running Hadoop, do you get a benefit? Is there a difference? Interestingly, for multi-node jobs, we were starting to see 3 to 4x difference in performance, and at those benchmarks personally, so I can talk to it. And then the AI buzz hit, right? We had to start coming up with GPUs, with NVLink connected GPUs and so forth. still single node level, and we came up with some concepts around CS Storm where we said, let's design the software stack so that it gives you the performant version, and then we slowly moved towards the GT version, which is the PCIe version of the node that the NX did with NVLink. And so over the years, 6, 7 years or so, what we've done is taken these open source components that were built for the big data problems that were openly out for community development and so forth. We have started implementing them so that it works in the supercomputers. So we call that product line called the Eureka line. And so what started off as a software stack on the GX, which was a simple cluster with the HPC interconnect, now runs, scales, and works just fine on any supercomputer. Going forward for Shasta, both the Eureka CS and the Eureka XC is going to merge into Eureka Shasta. And what it's going to contain is 2 different components. It's going to contain the way you launch jobs, and it's going to manage how you launch jobs. It's going to manage how you work with the different kinds of APIs that are new to the HPC world and so forth. And the 2 components are basically the analytic services and the manager. So the analytic services, you want to think about them as what you used to with programming environments, the compilers, the libraries, tools, the frameworks. The Eureka manager is the one that's going to decide how you take a system, how you partition them, how are you going to design workflows that have multiple requirements with heterogeneous components in it, and how are you going to launch jobs doing it. And this is traditionally how we think about Cray. And so we start off at the bottom, where every time a new technology comes out, we are playing with it in the lab. You're making sure that we eke out the last possible thing out of the machine and of the component. And once we have the component benchmarks that we have done, we try to build the nodes that best represents or that best utilizes those components. And then we try to put many of those nodes together, and we pretty much do the hardware part well. So what we've started doing a little bit better in terms of convergence to enable productivity is that supporting software that's open source, that's the top layer where you're seeing the application interfaces. So I'm going to take a, there you go, on this one. And then the more interesting pieces that are new to the HPC world are the system interfaces, where we're coming up with these ideas of how do you move data, and how do you move data on this memory hierarchy? How can we make it easy so that you don't feel the pressure of having to write code every time you're porting something that's out there in the public, in open domain? The second component that you see over here under system stacks is the ability to launch containers, ability to bring code to data, and bring code to data in a secure way, and so forth. And the last one is having cloud-friendly ways of launching jobs, cloud-friendly ways of resource management, and so forth. And the key tenets for doing that is that when we have a community that's working on the machine, we want to make sure that they're finding it easy to move data. The components that they're spending most of their time on just preparing data for launching big jobs is a lot more simpler, and that they're able to bring in the domain-specific creativity to express something that's unique to their domain in an easy way. And the third component I talked about was scaling up the workflow itself. So as you go through the process of, I'm going to be acquiring data, maybe from simulations, maybe from whatever source that I have, a light source or a scattering source or whatever it is. And then I'm going to be doing that job on my storage system, and then I'm going to be using a different part of the computer to do the AI training or the simulation feedback loop that Rob was talking about. Or I want to be able to take those trained models and put it at the source where the data is. And so given that workflow of starting from data and supporting it through the process of training and simulation and then actually being able to draw insights out of it, you've got different options down there. And different options where you turn your knobs to say, I'm interested in just serving up data. I just want to build a portal that thousands of users can ping every time. So that system would look a lot different. You would pick a lot of different other knobs from there, and it would work just fine. Or you could say, I want to design a system that's only strong scale. Or I want to design a system that's only throughput. I'm going to have hundreds of users on single node jobs. Now, how does that change the way you think about building your system, right? So we're going through that process. You can actually go through this process with most of our sales folks, and they can help you configure the system. And this is kind of how we do it after you have the system. So the top layer that you see is the layer that's a single node kind of software. So if you're trying to use TensorFlow on your laptop and you're trying to run it on a node on a Cray machine, you've got the exact same environments. You've got the Jupyter notebooks. You've got frameworks like PyTorch and TensorFlow or TensorBoard that works on top of TensorFlow and so forth. You're able to launch a Spark cluster on demand. You can use Keras over TensorFlow as well. And then the second layer is where we bring in the Cray secret sauce, where you're able to now, with 2 or 3 lines or minimal lines of code change, able to use the parallel environments that we support. And so, for example, if you're using deep learning with TensorFlow, the out-of-the-box version uses gRPC. We would plug that in with our own version of an MPI-based plugin that uses that increases your scalability efficiency by 30% or so, and things like that. So that's the parallel layer. And then right below the parallel layer is how we feed data to the layer on top. So if your data is sitting somewhere else, and you want different mechanisms to meet your latency requirements, we've started supporting different ways of doing I/O, different ways of moving data, because now I want to talk about in a second how different kinds of APIs and different kinds of memory architectures are going to help. And so the level 4, where now I have a workload, and I want to make sure it's an HPC workload. I've built the system for HPC workloads, but now I have a new need where I have AI coming in. I need to make sure I have the best system for my AI component of the workflow. So just like we did with HPC before, we have looked at about 60 different startups that have come up with their own ASICs, their own software stack that goes with it. And we've done most of the due diligence work and supporting them and so forth. So if you have a workload and you're saying, hey, I need this much of inference, I need this much of training, and I need these secret sauces that each of these processors are coming up with, and my workload is an LSTM, or my workload is a CNN, or my workload is a GAN, you're able to come up with the optimal architectures for it. So real quick, just to show you quick updates on some of the things that have been out here. So Habana is a company from Israel that launched its processors, I believe last year. They came up with a training processor this year. Compared to an NVIDIA, we're seeing a lot of benefits already going on there. So this is, until so far, I talked about, just by system thinking, just by the design process of how we build systems, I showed you how we could go from building a system, running software productively, being able to scale that software that you just wrote, and then have the system that you want to build using off-the-shelf components. Now I want to talk about what is it that we are doing at Cray that makes it uniquely differentiable. And so the first one is obviously the interconnect. I don't have to talk about Slingshot. I'm sure most of you have heard about it in the announcement that have come out. And so what it is designed to do, in my perspective, is 3 things. So if you were to design a system only for HPC, your node would look more like the one on the right over there. It would have high precision. It would have the vector extensions that you need. It will have the high bandwidth memory that you require. It requires I/O over memory hierarchy. And it's typically working based on code that you optimize in a static way. It's the C++ Fortran compiled way. Versus if you're in the big data space, you're okay with mixed precision. You're okay with FP16. You're okay with some of the other floating point representations. You need a lot of RAM if you're trying to do analysis in memory. And you probably want a few of these ASICs to just sprinkle in there depending on the different requirements that you have. You prefer persistent node local storage, and you do just-in-time compilation. Right? So given these 2 worlds, and given how data is going to flow, we had to come up with different ways to support the data flows and the patterns that both of these kinds of workloads are going to represent. So this is where, on top of Aries, where we had the adaptive routing, we've added congestion control. So some of the preliminary experiments that we've been doing, we see anywhere between 2 to 20 times when you run parallel AI workloads and parallel HPC workloads on the same machine. And so if you turn the congestion control on, you're starting to see that for many, many workloads, you see a lot of difference in how it converges. And so there's a paper that's going to come out at Supercomputing where we talk about those converged workloads and the differences there. And the third component is also the traffic classes. So where we're going to give the user facilities the ability to pick and choose who needs to be prioritized during the time of execution. If somebody has a bad code and is bringing everybody else, you'll have the knob to say, hey, tune him down so he's not disturbing everybody else. So it's high responsibility, but we hope that it'll be a feature that people like going forward. And so the next idea that we're supporting is enhancing our programming environment. So you've traditionally seen us do the multi-threaded way of MPI supports, the MVAP and so forth. And what has happened since looking at these AI converged workloads is that we are now having to support both data parallel movements, and we're having to support the ensemble parallel worlds. The ensemble parallel worlds mostly driven because when you try to bring in the HPC world and the AI world, now we are trying to merge 2 concepts of uncertainty. The uncertainty that comes in from your traditional simulation, PDE, convergence, numerical world, and then the uncertainty that comes from the choice of your model with AI and so forth. And so we see that when you do have converged workloads, you need APIs that support all 3. And then anytime somebody goes from an internode to an internode problem, it's becoming much of a bigger deal in terms of code portability and so forth. The third benefit that you get out of the Shasta architecture is that Your traditional system with HPC, you had a separate file system, then you had a separate compute system, and every time data was moving in one direction from the compute to storage, and when you needed to do the analysis, you were taking the data to a different cluster and doing stuff on your own. With Shasta, they're all going to be on the same high-speed network. So the bandwidth of the interconnect is going to make sure that you're able to do your seamless workflows on the same machine, irrespective of the different components that are there within the system. So you can pick and choose different hierarchies. You can configure a system with different levels of performance and expectations based on your budgets and so forth on the same system. It's all going to look like it's one system that's big. So in terms of benefits, again, it's going to be lower cost than having two systems. It's going to be less complex to manage, and it's going to be a lot better because in terms of performance, everything is closer to where compute is and where you want your data to be moved. The fourth component I want to talk about in terms of what Cray has done to differentiate themselves is that we keep up with where everybody else is in terms of hyperscalers. So one of the reasons that Rob was mentioning was people go to the cloud because they are kind of the pioneers both with hardware and software. They buy hardware before everybody else. They have software updated very fast and so forth. But then when you're trying to build something that's on-prem, because you can't move data to the cloud or it's just too expensive for you to do it, we need to make sure we keep up to date with what's going on. So if you think about the promise of what hardware vendors are telling us, anywhere between a 10 to 1,000x improvement in the next year and a half on deep learning, right? Compared to what has happened in software, we already see 7 to 10x improvement, one coming from each vendor, be it NVIDIA, be it Google, or be it Baidu, whoever it is, that make tweaks on the algorithm side and put it into their respective frameworks. And then the cost has gone all the way from, hey, I want to solve this problem, it takes me 4 days or 6 weeks or how much ever time it took, to I can do this at spot pricing on AWS, right? And so the hope is that as these kinds of algorithmic developments are happening, people get comfortable to build bigger, better models that can be trained on a bigger machine and at better accuracies and so forth. So the last part is a subtle difference in how Cray's approached codes before and optimizing and tuning codes to how we're thinking about it now. So earlier, we had a niche and narrow focus on Amdahl's law concept, where if you had a code, we were able to break it down into components that were moving data, components that was doing compute, and then we figured out how do you parallelize the compute components, what's the best scale up you can achieve, and so forth. We were doing it within a particular code and within a particular kernel. But what we've seen with this converged workflows is that people just don't use one code anymore. They use 6 or 7 different tools from going from here's where my data is to here's where my insight happened. And so somehow we have to figure out a way to make sure not only do we support these multiple tools, but the opportunity to optimize each of those tools is also possible with the different API support and so forth. And so I wanted to quickly summarize, just like Rob did, with how are some of the customers using these tools. The first example is with growth in compute, with growth in the data sets and the availability of labeled data sets and so forth, there is a significant increase. So going from the AlexNet model that won the ImageNet competition all the way to the most recent StarCraft, OpenAI says there is about 300,000 times increase in compute. So the supercomputers are already there. And if you're still in the process of building Megatron-like models, it's the 16,000 GPUs were there in Titan 6 years ago. And so you could have built the Megatron model if you had the need 6 years ago on a supercomputer. And so if you had a supercomputer today, you're literally building models of tomorrow. In science, we are seeing that scientists are becoming very, very creative. And so one of the differences between the commercial data of cats and dogs versus the scientific side is that the shapes of data are quite different. So you're starting with points, starting with meshes, starting with unstructured data points that are remotely connected or connected on demand and so forth. There is molecular data with some dynamics associated with them. There is omics data that are sequences, and then there is the combinations of multiple versions of these. And then it's not very trivial to say, I'm going to take a ResNet-50 model and apply it to genomics, or I'm going to do what LSTM do for time series analysis, because your scientific data typically has a lot of other variables associated with it. You have the 3D structures, the 4D structures, the ND structures, and then you've got the sparsity assumptions, you've got some physics assumptions, there's resolution issues and so forth. And so people are trying to do so many things with transforming data that goes from this format to something that's meaningfully vectorizable for scientific discoveries. And then a quote that from Oak Ridge, from Sergey Kilinin, he's a scientist there, is that big data helps you get to correlations pretty fast, but then going from correlations to causation is combinatorial, right? And so where AI is being really used in most of the cycles the converged workload is happening is that your forward simulation tells you certain things, Your data tells you certain things, and now when you're trying to bridge that correlation to an explainable option, you're trying to use different ways to generate hypotheses that tell you how you interpret that result. And so AI helps you do that, right? So you can do feature-based search, where you know a predefined template you're searching for, rather easy problem. The second kind of class of problems is you have data, you're looking for a space with zero electric field, or you're looking for pockets of areas that you want to numerically solve and so forth. And the last set is basically saying, I don't know anything about the data, can you just mine the data to tell me what patterns I should be interested in? So irrespective of the kinds of methods you're using, the benefits are as follows, right? So when we tried doing the 4 things that we typically do with HPC codes, which is take the application, optimize for Amdahl's law, try to make sure your collectives for the interconnect are mapped back to the problem, and then you're able to use some of the algorithmic cleverness, we find that with graph analytics, we're able to handle 1,000 times bigger data sets with up to 100 times faster than any other database that's out there. With matrix methods compared to Spark and in memory, we get about 2 to 26 times better performance of the same systems. And then with deep learning, we are able to guarantee that we get up to 95% scalability efficiency that reduces training time. And so in terms of successful workflows, I've got about 4 minutes. So I'm going to quickly summarize some of the events. This is a slide from Prabhat at NERSC. And so this is a suite of experiments that have already been done as part of the collaboration we have with NERSC at the Big Data Center. We've tried to work on different types of data just to get the feel for what's going on and where are the actual benefits of AI and HPC convergence. So we've looked at galaxy data, we've looked at cosmology maps, we've looked at audio signals, we've looked at particle tracking data, and each one of them required custom development of models. People started off with the ResNet kind of a model, and then they would go take a step further, make it something more specific, and they've made progress along the way of making bigger models and so forth. So the first use case I'm going to talk about is integration with facilities. I think Rob had a slide about this on CERN as well. And so this was a use case where data streams in at about 800 terabytes at the source, and they had a cluster there that was actually processing the data all the time. It took about 20 scientists over 10 years to design the scientifically inspired feature extraction method to show which data is good and which data is bad, and then throw the data that's not good. And so when you take that system, which requires a cluster of 100 CPUs to be able to process all of the data to the latency requirements that they needed, with one inferencing model, you've already saved flops. Right? But you needed the labeled data before. So what the story that came out of this is that if you're trying to classify the 4 kinds of particles to know which data sets to keep and which data sets to throw, this was a model that was based on 10 years worth of work that now replaces it at 3 orders of magnitude lesser compute requirements. Right? So that's improvement from AI. In terms of accelerating the deep learning training itself, so these are the use cases where people are trying to build surrogate models. So if you're doing fluid dynamics and you don't have the compute cycles that you can buy or you can use, you're trying to get away with some low resolution models. Now, can you build an AI model that replaces your physical model, and you want to be able to train it fast? Our tools help you do that. So I talked about the 95% scalability when you're training deep learning in a distributed way. We also have tools that are used for the hyperparameter optimization, which helps you pick the right model. So if you have access to a supercomputer and you're able to launch several of those throughput jobs in parallel, you can now search for different types of architectures in the neural network space and say, hey, by the way I'm propagating these neural networks in an intelligent way, I can get to the answer in 1/3 the time I would if I were to run it for an exhaustive search problem. And so I talked about those use cases with different kinds of data, being able to interpret them in different ways, interpret them in different, in creating new hypotheses and so forth. This was again an experiment at NERSC where 3 different methods: non-negative matrix factorization, principal component analysis, and I think it was C4.5 or 4.5 algorithm that was also done, where we compare what Spark does on the same machines versus replacing the Spark's matrix libraries with a Cray PE, and what the difference is. And you're seeing anywhere from 2 to 25x difference. And so the last use case is where the merging is actually happening on the theoretical side, where this was a use case with PGS, where we were trying to get to finding the 3D structure underlying the full wave inversion problem, right? And so the way people were doing this before was they would collect real data, and this is an example that I'm going to show you on the ground truth benchmark data set. And so what was happening was you would run a conventional full wave inversion problem, and you'd get an answer that looks something like that on the middle. But then what happened was that we worked with some of these guys and figuring out, can you use machine learning to try infer the inverse model initialization itself. So if the 3D geometry was your variable, can you now somehow figure out how to solve, what is the optimal geometry that corresponds to the observations and the forward simulation you're doing? And then this is what happens as you're converging. So the video, hopefully it's playing over there. So it's trying to learn the 3D structure as it's going, and eventually it comes back and says, hey, here's the optimal 3D structure that based on the forward model that you gave me for the full wave inversion, the best solution is this. And you see how close it is to the benchmark data set there. So I wanted to conclude with the following thoughts, right? The way we've been thinking about systems for the future in the exascale era is that you're going to have Cray think about general purpose flexibility. So you're going to have commodity-like configurations, but it's still going to be custom processors and chips. You just don't feel the difference. It's going to accommodate seamless heterogeneity. It's going to have an interconnect that supports both the Ethernet compatible and HPC compatible APIs. And we're moving more and more towards looking like the cloud. So if you knew how to use and write and program for the cloud, we're starting to think about how do we support similar kinds of microservices on our supercomputer. And in terms of what it is that we're trying to optimize, it's about the end-to-end workflow. It's about where data lives, how data moves, and how you're able to use the data to come up with better insights and so forth. So with that, I'll stop and thank you for the attention and open up for questions.